to remind you of our goal today. So we are discussing the same paper we've been talking about for this whole mini course, the same title of the mini course, joint with Sam Mellick and Mikolaj Fraczyk. And today we are going to finish the sketch of the proof that the Poisson point process on G has cost 1. Okay, so G, for today, we are just going to think about G as a higher rank semisimple real Lie group. Okay, and we'll sketch the proof that the Poisson point process on G has cost 1. This implies, by things we've discussed earlier in the mini course, that G has fixed price 1, which implies vanishing rank gradient. Okay. All right, so yes, let's. We'll start by talking a bit more about this ideal Poisson Voronoi tessellation. So as we mentioned, this was first introduced in a paper of Budzinski, Curie, and Petri. And then there was, okay, so they introduced this object to study, to get a bound on Cheeger constants for hyperbolic surfaces. But they did not formally construct the object. So then in this work by these 4 authors, which I might refer to as a KELU, just as an abbreviation. Okay, so this was put on the archive in 23. It's now accepted for publication. And then also our paper. Okay, and the approach that we take in these 2 different papers, we did it independently of each other. We take a slightly different approach in constructing this object. In this paper in particular, they do it, okay, we both do it sort of in more general of a space that we actually look at, we focus on in the papers. They focus on hyperbolic space in this paper, and they have many lovely illustrations that are very good for getting familiar with this object. So I encourage you in particular, if you haven't looked at a figure that I included in the lecture notes, to look at that now. That will help a lot in this lecture, or you can go directly to their paper. But I'll describe this a little bit, just hopefully it won't take too long, and then I'll go through an explicit construction using what we did in our paper. Okay, so the idea and these 2 ideas should be equivalent, but a proof that they are equivalent has not yet appeared. So the idea in this paper is to take a limit. Okay, let's just think of H2 as our space for now. Take a limit of Poisson point processes on the hyperbolic plane. Okay, so we're going to consider a sequence of them. They have intensity alpha, and then we're going to send alpha to 0. Each one of these Poisson point processes has an associated Voronoi tessellation. Okay, so this is just the nearest neighbor tessellation. Poisson point process, remember, is a discrete collection of points in our non-discrete space, H2. So we do a Voronoi tessellation there. And So we also have this limiting sequence of Voronoi tessellations attached to these Poisson point processes. And in this paper, they prove convergence of the Voronoi tessellations to a limiting tessellation object, and they prove exactly like the distribution of that object. They describe it explicitly for hyperbolic space. And, okay. It ends up, you can think of it, how we think of it in our paper especially, is as a Poisson point process on a boundary, but it's just a bit of a non-standard boundary because it's non-compact. Okay. So it lives on, okay, part of where it lives is the Gromov boundary, but then we also pick up an R fiber at each point. All right, so the way that you can think of this intuitively, all right, so we have a limit of Poisson point processes on H2. And you can think of like each point in that process is not just a point, but sort of a path. So we fix an origin in H2. Okay, and then as these process points escape to this boundary, they escape to an angle, like an element of the Gromov boundary, space of ends. But you also keep track, somehow you have to also keep track of this R fiber, like sort of the difference between where this point started somehow in the hyperbolic plane and the origin. So that's what this R fiber is doing. So think of it as a time delay. Okay. Questions? Sorry? So you should think of it as a time delay. And, okay, so we will end up with a collection, a discrete collection of random points on this space, the Gromov boundary across R. And one way you can think of what that R fiber is doing is it's tracking, so these points end up on the boundary as a limit of Poisson point processes on the space H2. One way you can think of this R fiber is by, okay, so these points like start somewhere. Okay, they converge somewhere. The R fiber tracks where they start compared to the origin in the space. So explicitly, all right, so you can still think of H2, or since we will be talking about higher rank, you can think of H2 cross H2, or the symmetric space for SL3R. But this construction works for any, we're just going to, in our paper, we said non-amenable LCSC, locally compact second countable space. We want a isometry group, so we'll also think of a G invariant measure, or yeah, G invariant measure and a G invariant metric on X. Really, what we use to get a non-trivial limiting object is exponential growth. And 5 authors mentioned in Akelu, really all you need is super polynomial growth. Okay, and that's just to get some sort of interesting boundary for the Poisson point process to live on. Okay, so we are going to embed x into the space of continuous functions on x. So we do that by sending a point to this distance function. So this is the idea. We're going to modify this. But this is useful in a couple different ways. So one way is that this space of continuous functions on x has a natural topology, compact open topology. And we'll use that to take the compactification of this image of x. Also, on the other hand, x has a G-invariant measure. So we use the push forward measure to get a G-invariant measure on the space of continuous functions. Okay, so we'll think of a limit. So we'll take an embedding for each t and r. Okay, and then we'll send, we're just going to add in this t, and actually, okay, maybe we should think of it like this instead. Okay. So t is going to be the analog to this time delay, and it's what we'll end up with in the limit. You can think of it as a space of generalized Boozman functions. So one specific t is the distance from x to the origin, and that particular t gives you a Boozman function. But we need a G-invariant set as a boundary, so we're just going to allow that value to vary, and that is how you also think of this time delay. Okay, so we'll take the closure of the space of all of these embeddings. Okay, the space of continuous functions on x. And so this is our space, then our measure we'll take a limit of push forward measures. Okay, so let's call this call our G-invariant measure on x for volume. Take these push forwards, and we'll normalize. Okay, by the volume of a ball of radius t and x. So this will push all of the volume to the boundary in this closure. Yeah. Okay. So this sequence has a subsequential limit. We'll take one of those. We'll call it mu. It's G-invariant. Okay, and then this naming, we call this the corona space. The term corona first showed up in the Akelu paper. And I heard last night from Matteo, it's not meant to have anything to do with the virus. Instead, it has something to do with, like, I don't know, these are like mid-century like mirrors with the rays coming off of them. Okay, that's fine. Also, there's a very nice illustration that looks sort of like a solar corona object in the Akello paper. Okay, so we call this our corona space of X, equivalently G. We'll just switch between thinking of X and G. So our perspective in our paper of this ideal Poisson Voronoi tessellation okay. Right. So that definition above comes from Akello. This definition comes from our paper. So think of it as this Poisson point process on the corona space. It induces this Voronoi tessellation naturally on the space X. All right, so let's remember our goal. We want to prove this Poisson point process has cost 1. Okay, one more thing. We really use the Lie structure of G in our proof. So we prove that this corona space for, okay, so G is doesn't need to be higher rank just for this property. We'll get to the higher rank later. This corona space is isomorphic as a G space, so with respect to the G action. It's isomorphic to this space. Okay, so what is this? Take a minimal parabolic subgroup P in G. So if you're thinking of SLN, that's that you can take the subgroup of upper triangular matrices. And it's not unimodular. We need to mod out by a unimodular group to get a G invariant measure. So this is the maximal unimodular subgroup. In a minimal parabolic P. Okay. So in rank 1 or hyperbolic space, it's equal to the unipotence, but not in general. All right.
Is there any intent to use a tilde?
Okay, so I am not a Lie theorist or a geometer myself, but I've been told by many people that U is standard notation for unipotent matrices, and this is not in general unipotent matrices. In our paper, it is U. Okay. So now, proving the Poisson point process on G has cost 1. Let's think about this Poisson point process a little bit. So remember, the Poisson point process is a random variable on the space of all locally finite sums of Dirac point measures. So a realization, a sampling of the Poisson point process on our boundary will be exactly that. Okay, so for some locally finite collection, I'll call them beta i's. They're generalized Boosman functions. And G mod, okay, I'll also just say G mod U. So some important things that we will use. Okay, first, of course, this beta I is a function on X with output in R. We also prove, as a lemma in our paper, we use just the fact that X has exponential growth and the construction of mu. So we'll just use these properties, we'll use these properties. Take the measure of the set of beta in our boundary such that if we plug in the origin, it's less than or equal to 0, this has measure 1. And also, if we fix some constant C and R, take the measure of all beta such that we plug in the origin, it's less than or equal to a constant C, that measure is finite. Okay, so these sets are well behaved. Our measure is well behaved. So now I'll define a cell in the ideal Poisson Voronoi tessellation. Okay, so we have our set of points beta I in our Poisson point process. We'll just call this cell beta I. Okay, so we'll call this set B. The set of our Poisson point process points. And then all of the points that are closer, whatever closer means in this sense with this generalized Boosman function to beta I than any other point in our Poisson point process, those all belong to the same cell. Then we take the collection of these cells, that's the IPVT. Okay, and if it's important for the application that you're working with, you can introduce a tie-breaking function. It just has to be G equivariant and measurable. It's not difficult to do. So you figure out where to send points on the boundary. But we won't need to worry about that. Questions?
Do you mean that that's a binding or that's more like the facets?
It's a binding. Almost really too much easier. Yeah.
Is it easy to see that the cells are convex and they describe their boundary?
I'm not sure. I'm not sure they are convex. Maybe they are.
I wouldn't know.
Yeah. So, okay. So yeah, I guess the answer is no. They might prove something like this in a Kalu. Okay. These cells are infinite volume.
They are in rank 1 and not in higher rank.
It's two inequalities.
Oh, yeah. No. Also clear.
Okay. The behavior of this object is very different depending on if you look at it on Euclidean space, then it's a trivial object. If you look at it on hyperbolic space, you can see the very nice illustrations in the Akalu paper. If you look at it on a higher rank space, something very different happens, and which allows us to prove cost 1. So this is what we prove. Okay, so now G has to be higher rank. So G is a higher rank semisimple real Lie group. So we prove almost every pair of cells in the IPVT on a higher rank space shares an unbounded border almost surely. And we'll sketch the proof for this. Almost surely is with respect to the law for the Poisson point process on the boundary. Almost every pair is a technical detail. Maybe I'll mention it briefly. Okay. Before we do the sketch, I'll just give an overview of how we prove cost 1 from here. Right, so Sam talked about this yesterday. If we take an independent coupling, so we take a Poisson point process on G, we take an independent ideal Poisson Voronoi tessellation on G, considering them together does not change the cost of the Poisson point process on G. Okay, so and we'll use this. So we want to prove the Poisson point process has cost 1. We use the extra information from the ideal Poisson Voronoi tessellation to do that. This is allowed because it's like a sort of a weak factor of a Poisson point process due to details that Sam mentioned yesterday. If we just look inside a cell, so we take our Poisson point process, independent IPVT, we look inside one cell, then the Poisson point process on G restricted to that cell has cost 1. All right, so I won't talk much about this since it's in our paper, but really it's just an old result from descriptive set theory. From Kahn, Feldman, Weiss. So in this talk, we are going to talk about what to do. So we have this. Okay, and remember when I say cost 1, okay, what I mean by that is we can find, okay, so in general, for the entire Poisson point process, for cost 1, we take the vertices of the Poisson point process. We want to form a graph, a connected graph out of those vertices. We need to do it in a G-equivariant and measurable way. And cost 1 means that on average, this graph is going to look like Z. So that's what we're able to do that inside cells because, okay, Kahn-Feldman-Weiss says that because we have an amenable action, because we're looking at the action of G on G mod U, this restriction is hyperfinite. This lets us have cost 1.
I mean, it should be said that we apply this Kahn-Feldman-Weiss, but we have to prove something in order to apply it.
Sure.
Yeah.
So this uses that U isn't, or utility. Yeah.
Yes.
Okay, so now let's sketch this theorem. All right. Oh, also I just want to mention a nice reference for cost. Cost for countable groups, which helps to get an idea of cost for non-discrete groups as well. Sam and I both mentioned papers of Gaborio, which are also good references, but another reference is this short book by Kekris and Miller. Topics and orbit equivalence. Okay, so for unbounded borders, we're going to fix 2 points in our boundary. So this will correspond to imagining 2 cells of the ideal Poisson Voronoi tessellation. So we'll call them beta 1, beta 2. But really, we're going to use some dynamics here. We want to use this structure. So we'll just use this form. Okay, so these are U tilde cosets. And take a point. That's equidistant from beta 1 and beta 2, meaning just plug in x and it's equal. So if we're thinking about the ideal Poisson Voronoi tessellation, this setup is necessary for x to be in the cell of beta 1 and the cell of beta 2. But we also need it to be closer to both beta 1 and beta 2 than any other point in the whatever Poisson point process we have on G mod U. So we'll consider the stabilizer under G of these 2 points, beta 1 and beta 2. Call it S. So with the structure, we can see exactly what the stabilizer is. And you can prove, this is a lemma in our paper. The stabilizer is isomorphic of 2 r to the real rank of g minus 1 across some compact subgroup, which we're not concerned about. All we use is that in higher rank, the stabilizer is non-compact. So we're going to act on X by S. And okay, so the point is we're going to show that an unbounded subset of what we get when we act on X by S is contained in this boundary between these ideal Poisson Voronoi tessellation cells. So we'll just set up some notation to do this. All right, so we set this up so beta 1 of x and beta 2 of x are equal. So now this is just some fixed constant c. And let's look at this set. Set of all beta and g mod u tilde such that beta of x is less than c. So these are the points that in our boundary that are closer to x than beta 1 and beta 2. And we said before we'll use this in the proof that the measure of A is finite. All right. We want to consider the probability that, right, so let's let pi be a Poisson point process on our boundary containing beta 1 and beta 2. All right, we can do this. This is a valid thing to say because of the POM measure, which I won't get into the details, but this is also why in the theorem that's where our almost every pair of cells comes in. So we consider the probability that our Poisson point process on A is empty. Okay, so the number of points in A is 0. We can say explicitly what this is, just using the definition of the Poisson point process. Let's just assume we have intensity 1 for simplicity. This is just equal to e to the negative measure of A, which is greater than 0. So now we'll consider this along the orbit of x under S. We'll take an escaping sequence in S. And think about what you get if you take Sj applied to the set A. So we use our G action on the boundary. So this is equal to the set of all beta and g such that beta of sjx is less than c. And then if we consider the same sort of thing, probability that our Poisson point process does not contain any points in the set. We have our G invariant measure, definition of Poisson point process. This is always equal to e to the negative mu of a. We're going to use Borel-Cantelli. So just some notation, we'll say EJ is the event that our Poisson point process misses the set SJA. Sorry. Okay. But whenever this happens, this point SJX is in the shared boundary between the two cells. Okay, so that's the important point. And, all right, so one thing we can do, this is not necessary to argue this way, but it is sufficient. We apply the Hall-Moore theorem, and this tells us that if we go further and further into our escaping sequence, these sets SJA are almost disjoint from each other. But from the properties of the Poisson point process, this means our random variables, pi of SJA, are almost independent from each other. So the EJ are almost independent in the limit. So this is enough to apply Borel-Cantelli. So we take the sum of these events, or a subcollection of these events AJ. The probability that they occur is this e to the negative mu a, so that sum is infinite. Borel-Cantelli implies EJ occur infinitely often. And that's the proof.
I mean, you can also skip this Borel-Cantelli stuff by applying Poincare recurrence. Once you have that this event occurs with positive probability. Because the orbit under S occurs infinitely often.
I mean, that is Borel-Cantelli.
I mean, this is also not Borel-Cantelli on the nodes, because these are almost independent. So you have to apply this refined version.
Other questions? Okay, so let me draw a picture.
All right, so if you looked at the illustration and the lecture notes from the Mikolaj paper, you have an idea of what the IPVT looks like for H2. But, okay, and you can see in that picture, and I believe they prove in the paper that borders between cells are bounded. Not only that, certainly if you pick any pair of cells at random, they don't have to touch on a border at all. Okay, so in higher rank, right, I'm saying something very different happens. So it's not so easy to visualize. Okay, but the idea for what we're doing in this theorem, an H2 cross H2. Okay, so let's take a pair of boundary points. Okay, so I'm going to change my notation a little bit from what I did before. Okay, I apologize for that. So beta 1 and beta 2 are now just points in the Gromov boundary for H2. And our boundary point is going to be some that pair of points, and also some time delay. We'll call that m. So you can imagine, like we have these Boozman functions, and we're adding on some real value m. Okay, so we'll take another boundary point. Consisting of gamma 1, gamma 2, along with a time delay n. And okay, think about the geodesics connecting these guys. Pick a point equidistant from the pair. Okay, so just for the purposes of me being able to sketch this picture, I'll pick a point that's on these geodesics. It doesn't have to be. And then to see this unbounded stabilizer action that gives you unbounded balls, just do the diagonal geodesic flow. So in one coordinate, we'll go towards beta, and in the other coordinate, we'll go away from beta. This fixes our pair of boundary points, and you can see the unbounded stabilizer. Okay, so I have some time left. That's the main point of everything I wanted to say. So I can say some other things. I could give the definition for cost in the non-discrete case, so you can see that. Or if you have any questions, do that.
Yes.
This is kind of going further back a little bit. What is the measure of like all the betas so that beta of 0 less than 0 is equal to 1? I think I missed. I think you did mention that at some point.
Yeah, so I didn't say why, but you can, I'll say it's an exercise. You can do it. It's by a construction. So I don't know if this is still somewhere on the board, but yeah. Okay. Yeah, it's by construction of the measure mu. You can do that calculation.
Can we measure like the beta of x1, x2 by measuring the function of the plus m to beta 1?
Okay, so it depends on your metric. So that's what happens if you use the L1 metric, which is, okay, so Matteo Diachil has another paper just on H2 plus H2 where he uses the L1 metric. In our paper, we use the L2 metric, so in that case, I'm not sure if it's that simple.
Yes.
Could you draw on the picture the corresponding cells with just these two beta and gamma?
No. I'm sorry.
That's fine.
Exercise. Okay, so I'll just write up the definition for the cost of a Poisson point process, then you can see it. All right, so we no longer need to just think about semi-simple Lie groups. We can do any unimodular, locally compact second countable space. So let's call it X. This is due to Mikolaj and Sam. Okay, so let's call our Poisson point process pi. And I give you a little bit more context. So also just think of a G action on X. So now we are in the situation that I mentioned in the first talk. So Poisson point process is a measure preserving dynamical system. Okay, so remember M of X is the space of all locally finite countable Dirac point measures on X. This P alpha means the law of a Poisson point process with intensity alpha. This is a probability space. And we have a G invariant measure on X. So this action is probability measure preserving. In particular, this action, so imagine you have a Poisson point process, a realization. Okay, so a discrete collection of points in X. You act on it by every element in G, and you get an orbit. So this action induces an orbit equivalence relation on the configuration space M of X. For the theory of cost for countable groups, the same thing happens. You consider the same thing. But for a countable group, you have it's a countable Borel equivalence relation, your orbit equivalence relation. In this case, it's not countable because G is not countable. But this theory of cost in the non-discrete world is really very similar to the theory of cost for countable groups. And you can restrict to obtain a countable Borel equivalence relation. Okay, so we take a subset of our configuration space. We take the subset containing all of the point processes that are, or all of these collections of Dirac point measures, where the Dirac point measure at the origin is 1. So this is a subset, and it has a nice restriction of the law for a Poisson point process. We put the Poisson measure on the space. Okay, so the Poisson measure for the Poisson point process is very nice. In fact, the Poisson measure is characterized this way for the Poisson point process. Okay, I'm probably messing up this notation, but the law for the Poisson measure is just the law for a Poisson point process conditioned on having a point at the origin. And it's for the Poisson point process only, it's a simple, you get a simple explicit description of the measure. This is due to the independence properties of the Poisson point process. Essentially, in some sort of limit, this point at the origin is independent of everything else in the process. Okay, so we'll call this Poisson measure P0.
By the way, what do you mean by countable equivalence relation?
Countable equivalence relation means that you have a countable number of
Equivalence classes?
yes. Or yeah, inside each equivalence class. Yes.
Otherwise, they're heard the graphs on.
Yeah. Yes. Okay, so we can still act on this probability space. We just take the G action restricted to, okay, maybe it's easier not to write this in general, but just for a specific element. So we just restrict our action to these elements of G, so that when we act on the point process, we just pull back each point to the origin. So that is a countable Borel equivalence relation. And then for cost, okay, let's see if I can actually write this. So you Mikolaj and Sam define cost for any point process. I believe, let's just do it for the Poisson point process. So pi is a Poisson point process. The cost, okay, we have this normalization factor of 1/2. Okay, essentially we're just looking to measure the average degree of a vertex. Okay, so we integrate, this is just an expectation. We can look at the degree at the origin in particular, because we have a point at the origin, and our measure is, what did I call it? The measure is our Poisson measure. Okay, so we'll need to take an infimum. and we look at all of the possible ways we can connect points of our point process in a geoequivariant and measurable way. We call those graphenes.
Questions? Further questions?
I wanted to check something. You mentioned two constructions that should be like are equivalent, but
Yes.
not maybe. That's one is that the limit, the ideal one. The other one is the point process you're doing, the one that comes from the point process you're doing in the Coronoi space.
Yes, so this Jagiellonian, Curie, and Enriquez lines, Unel, they prove explicitly convergence of tessellations. We do not prove convergence of tessellations. We just construct a measure, take a Poisson point process.
I see. So you sort of like already have an understanding of what the limit will be, and then you're like, let's just start with that. And
Yes.
Okay.
Yes.
So, and also I'll mention I included, it is an open question, it's a question in the Akalu paper. I put it as an exercise, but it is work in progress by Matteo Jagiellonian and Ali Kalezi, so maybe don't work on it.
That's just proving the equivalence of these two definitions, which is essentially just an interchange of limits.
Yeah, like some continuity of constructing the tessellations, essentially.
Right? Yeah.
Any questions?
So the integral with respect to the Pal measure there is what in the countable setting was the average degree, right? Or like in the definition of cost.
Can you say that again?
Yeah, the definition of cost for like countable groups, we had that was the infimum over 1 half of the average degree. Is the average degree in the countable setting what now is replaced by the integral with respect to the Pal measure? Okay, thanks.
Any last question? Let's thank Amanda and Sam for